Number 24. An engineer wishes to design a curved exit ramp for a toll road in such a way that a car will not have to rely on friction to round the curve without skidding. He does so by banking the road in such a way that the force causing the centripetal acceleration will be supplied by the component of the normal force toward the center of the circular path. A. Show that for a given speed v and a radius r, the curve must be banked at the angle theta such that tangent theta equals velocity squared over radius times acceleration due to gravity. B. Find the angle at which the curve should be banked if a typical car rounds it at a 50 meters radius and a speed of 13.4 meters per second. So we're going to start off this problem by drawing a diagram. So we have a ramp and we have a car, and we know that this angle is theta. Next, we're going to draw all the forces acting on the car, which are weight, and then normal force, which is perpendicular to the surface the car is on, which is the ramp. And if we connect these forces in such a way, we know that this is theta because that is theta. And because these are vertical angles, this angle is also theta. And then we can find that the component of the normal force going towards the center of the ramp is normal force sine theta, and the y component is normal force cosine theta. For part A, we're basically just deriving tangent theta equals v squared over rg. To do so, we're going to first sum up our forces in the y direction. So in the y direction, we know that we have the weight and the y component of the normal force. And because up is positive and down is negative, we can find that normal force cosine theta minus mg is equal to ma. But because there's no acceleration in the y, that's just 0. And we end up with normal force cosine theta is equal to mg. And in the radial direction, or the direction towards the center of the circle, we only have this component of the normal force, which is normal force sine theta. So we know that normal force sine theta is equal to the mass times acceleration, the centripetal acceleration. And centripetal acceleration is v squared over r, so we can substitute that. Because we know we have to end up with tangent theta, we can use this equation and divide it by that equation, because sine theta over cosine theta will give us tangent theta. And so once we divide them, the normal force cancels out and the masses cancel out, so we get that tangent theta is equal to v squared over rg. For part B, we're just plugging in values that the problem gives us into this equation. So we know that the radius is 50 meters and the velocity is 13.4 meters over seconds. So once we plug everything in, we get 20.1 degrees as the angle at which the curve would be banked if a typical car rounded at that particular radius and velocity.